Hi, this is Dr. Habib Ahmed, and today I'm going to demonstrate how to perform the Silvaco TCAD simulation of graphene and molybdenum sulfide based field effect transistor. Initially, I will give a brief introduction into this topic, followed by the Silvaco TCAD simulation of the transistor. So here is the structure of the transistor that I have simulated. And let us start with the basics. So first of all, what is a field effect transistor? A field effect transistor is a type of transistor that uses an electric field to control the conductivity of the channel in a semiconductor material. It belongs to the family of unipolar transistors, which means that the current flow is primarily controlled by the voltage applied to the gate terminal rather than the amount of current flowing into the gate. Let us talk about the conventional field effect transistor. In a conventional silicon based field effect transistor, we actually have a substrate. The substrate is lightly doped, and the drain and the source are heavily doped. So for example, in this case, this is an N-type metal oxide semiconductor field effect transistor, which means that the channel is made up of N-type materials. The drain and the source are heavily doped N-type materials. The substrate is lightly doped P-type. And similarly, we have a gate dielectric material. Then we have the gate contact. We also have the drain and the source contacts. Under normal operation under zero applied bias, this structure is going to be in cutoff, which means that the drain and the source are disconnected. We don't have a channel that connects the drain with the source. However, when we apply a positive potential to the gate above the threshold voltage, it's going to attract electrons from the bulk of the material, forming the channel between the drain and the source, turning on the transistor. Now, this is the structure of the conventional field effect transistor based on silicon. However, if we talk about the molybdenum sulfide based field effect transistor, its structure is quite different. So this is my simulated structure, and this is a not to scale layer structure diagram of the same structure that I have simulated. So the structure of a molybdenum sulfide transistor typically consists of several key components that enable its functionality as a field effect transistor. First of all, we have a substrate. Molybdenum sulfide transistors are typically fabricated on a substrate that provides mechanical support and stability. Common substrates include silicon dioxide, silicon, or even flexible substrates for applications in flexible electronics. So over here in our structure, we have a heavily doped P-type silicon substrate followed by a relatively thicker silicon dioxide layer. In this structure, we also have a gate insulator, which is a thin layer of insulating material, mostly silicon dioxide, but in our case we have employed hafnium oxide, and I'm going to tell you slightly later why I'm using hafnium oxide instead of silicon dioxide over here. Then we have a molybdenum sulfide layer on top of this insulator. So basically a few layers of molybdenum sulfide are deposited. Molybdenum sulfide consists of molybdenum atoms sandwiched between two layers of sulfur atoms in a hexagonal lattice structure. In a transistor, this molybdenum sulfide layer acts as a semiconductor channel through which the current flows. Then we have the drain and the source contacts. The drain and the source electrodes experimentally are fabricated on top of the molybdenum sulfide layer. However, over here we have placed them on the right side and on the left side for the purpose of simulation. These contacts are made up of graphene material in our case. Then we have a gate electrode which is placed above the molybdenum sulfide layer, separated by the gate insulator, which is hafnium oxide. The gate electrode is used to apply a voltage that modulates the conductivity of this molybdenum sulfide channel. By varying the gate voltage, the number of charge carriers in the molybdenum sulfide channel can be controlled, thereby switching the transistor between on and off states. Let us talk about the graphene material employed in our structure. Graphene is considered a zero bandgap semiconductor, or you can say a semi-metal rather than a traditional metal. Its unique electronic properties make it highly promising for applications in electronics, energy storage, sensors, and various other fields where its exceptional conductivity and other properties can be utilized. One of the beautiful properties of graphene is that it is stronger than steel of the same thickness, but much lighter as compared to steel. And despite its strength, graphene is also highly flexible and can be bent, stretched, or even folded without breaking. Another beautiful property of graphene is that it has a high electrical conductivity. Its electron mobility is around 100,000 to 200,000 centimeters square per volt second at room temperature. And this property makes graphene suitable for applications in electronics such as high-speed transistors and conductive electrodes. However, due to the zero band gap of graphene in its pristine form, it cannot be turned off completely in transistor applications without modifications, which limits graphene in its use in digital logic applications, but we can instead use it as electrodes in transistors over here. Also, graphene exhibits extremely high thermal conductivity, surpassing approximately 5,000 watt per meter Kelvin, which is a really good value at room temperature as compared to other materials. This property makes it promising for applications in thermal management such as heat dissipation in high power electronics, etc. Now, let us talk about the molybdenum sulfide layer used as a channel in this structure. Molybdenum sulfide is a two-dimensional material. Unlike graphene, molybdenum sulfide has a band gap of approximately 1.9 electron volts, which kind of changes to direct band gap for a multi-layer or bulk layer. It's going to be around 1.3 electron volts for in bulk form. This property makes molybdenum sulfide suitable for semiconductor applications including optoelectronics and transistors. The presence of the band gap allows molybdenum sulfide to switch between conducting and non-conducting states, which is crucial for digital electronics. Also, molybdenum sulfide has high carrier mobility exceeding approximately 100 centimeters square per volt second at room temperature, which is a good advantage for high-speed electronic devices. We can dope molybdenum sulfide as well to modify its electrical properties, such as its carrier concentration and conductivity, by introducing impurities or by applying gate voltages to this structure. So, molybdenum sulfide is used in a variety of applications including transistors, sensors, photodetectors, and energy storage devices due to its properties. Let us talk about another material used in this structure, which is hafnium oxide. Hafnium oxide can be used as a gate dielectric material in molybdenum sulfide based transistors, and it has been extensively studied for this purpose because hafnium oxide has a high dielectric constant, typically in the range of 20 to 30. If you compare it with silicon, the silicon dioxide, in fact, the dielectric constant of silicon dioxide is, I think, around 13.9 or 14. I don't know the exact value. I forgot the exact value, but I think it's around 13.9. So the high dielectric constant for hafnium oxide allows this material to form a thinner gate dielectric layer to achieve the same capacitance as thicker dielectrics with the lower dielectric constant. This also enables better electrostatic control over the molybdenum sulfide channel with reduced gate leakage currents. Furthermore, hafnium oxide has a good compatibility with molybdenum sulfide as well. Now, in this structure, you might see these a few layers of graphene over here, and this is used as a floating gate in heterostructure memories or in flash memories. In this simulation, I have included this layer. As you can see over here, here is a floating gate based on graphene. So I have included this layer, but I'm not going to utilize it in today's simulation. My focus today is going to be based on transistor and not on the memory part. But I have included it because in future I would also like to utilize it as a memory heterostructure. So I'm going to perform the memory-based simulation on the same structure at some point later as well. Now let me give you a slight intro into the floating gate. A floating gate is an isolated region within the transistor structure that is electrostatically isolated by a thin oxide layer from the surrounding substrate and other conductive elements. In flash memory technology, the floating gate is used to store charge, typically in the form of electrons. When electrons are injected into the floating gate becomes negatively charged. This charge can be retained for long periods even when power is removed, making it non-volatile. So basically we can form a non-volatile memory with this kind of structure. On the other hand, here we have got the control gate, and the control gate is actually used to control the operation of the transistor. By applying a voltage to the control gate, we create an electric field across the oxide layer, which modulates the conductivity of the channel in order to turn on or in order to turn off the transistor. So this was a brief introduction into this topic. Now let us switch to the simulation part. Before that, let me close this. So I start with Go Atlas. I'm going to perform the simulation in Atlas module of Silvaco TCAD. Here is the meshing part. My structure is running from 0 to 8 micrometers in the X direction and from 0 to 0.5 micrometers in the Y direction. As you can see over here, running from 0 to 8 micrometers in the X direction and from 0 to 0.5 micrometers in the Y direction. Here I have defined different regions for this structure. My region number 1 is hafnium oxide running from 0 to 8 micrometers in the X direction. So let me place these two side by side so we can see them. So my region number 1 is hafnium oxide running from 0 to 8 micrometers in the X direction and from 0 to 0.030 in the Y direction. So this region over here is my region number 1. Then region number 2 runs from 0 to 3 micrometers in the X direction and from 30 nanometers to 32 nanometers in the Y direction. So if I zoom in on this structure, this region, small rectangle over here, is my region number 2. Then my region number 3 is graphene, running from 3 to 5 and from 30 nanometers to 32 nanometers. This bluish kind of region, cyan region, is actually the floating gate, running from 3 to 5 micrometers in x direction and from 30 to 32 nanometers in y direction. My region number 4 is hafnium oxide, running from 5 to 8 micrometers along the x direction and from 30 to 32 nanometers in the y direction. So this small rectangle over here is my region number 4. Similarly, region number 5 is based on hafnium oxide. This region, this rectangle, extending all the way along the x direction and running from 32 to 38 nanometers along the y direction, is my region number 5. Similarly, my region number 6 is, so let me zoom in on this region. This small rectangle is my region number 6 based on hafnium oxide. Similarly, this small rectangle over here on the right is my region number 7, running from 5 to 8 micrometers in the x direction and from 38 to 39 nanometers in the y direction. So similarly, this was region number 7. Similarly, my region number 8 is based on graphene, and actually this source part is my region number 8 based on graphene. This channel part based on molybdenum sulfide is my region number 9. This drain part over here on the right side, based on graphene, is my region number 10. Similarly, region number 11 is silicon dioxide, this big region over here. My region number 12 is silicon. So this region over here is region number 12 based on silicon. Here I am defining the electrodes. I have set this electrode as the source, this electrode as the drain, this electrode as the gate, and I've set the silicon substrate to substrate. So at this point I save the structure. Then I start working in another module of Atlas, Silvaco TCAD. Here I am actually importing the previously saved structure. Here I have set the doping of region number 12, which is this silicon region, to 2 into 10 to the power of 20 p-type. Now we have to define the properties of hafnium oxide, molybdenum sulfide, and graphene layers. So as you can see here, I have introduced these different regions, but for your information, all these three materials, hafnium oxide, graphene, and molybdenum sulfide, are not built-in materials inside Silvaco TCAD. So we have to introduce them as user-defined materials. And I have already posted a video on how to include new materials into the Atlas tool of Silvaco TCAD. So for further details, you can go to that video to seek more help. And so I've introduced them as user-defined materials inside this block of code. And then over here, I've introduced the properties of these materials. Like, for example, I've introduced the bandgap of hafnium oxide, the electron affinity, permittivity. As you can see over here, the permittivity of hafnium oxide is pretty high. Then the density of states in the conduction and valence bands, the electron and hole mobilities, electron and hole recombination lifetimes, etc. I have defined these properties for molybdenum sulfide as well. As you can see, the band gap of molybdenum sulfide is 1.89 electron volts. Similarly, the band gap of hafnium oxide is 5.5 electron volts. As compared to silicon dioxide, its band gap is relatively smaller. For silicon dioxide, the band gap is approximately 9 electron volts. However, as compared to silicon dioxide, the permittivity of hafnium oxide is pretty high. Similarly, I've introduced the properties of graphene as well. And over here, so here is something like tricky. I already discussed that the band gap of graphene is 0, but when I tried to perform the simulation, it was giving me trouble. So in order to avoid that trouble and in order to perform the simulation, I had to give it a slight band gap of 0.1 electron volts. And then I introduced the electron affinity of graphene and permittivity, electron and hole mobilities, etc. for graphene. Here I have introduced the work functions for the gate, the source, and the drain. The work function of graphene is 4.5, and since both my drain and source are based on graphene, so I have set the work function of both source and drain to 4.5 electron volts. Here I am including different models for performing the simulation of the transistor. Here I want to look at different output parameters. I've included Newton method for the numerical simulation of the semiconductor device. Here I save the structure under thermal equilibrium and then plot the structure with this name under thermal equilibrium. In this block of code, I want to look at the ID versus VGS characteristics, the drain current versus gate to source voltage characteristics of the transistor. So I have set the drain voltage to 45 millivolts, and I am sweeping the gate voltage from 0 to minus 15 volts initially with a step of minus 0.5, and later between 0 to 2 at a step of 0.5. So basically I am running a sweep for the gate voltage from minus 15 to 2 volts. So this block is going to give me the transfer characteristics of the transistor. Then I have set the gate voltage to minus 6 volts, and I'm running a sweep for the drain voltage from 0 to 0.04 volts at a step of 0.005 volts. Later I fixed the gate voltage to minus 3 volts, and once again I'm running a sweep for the drain voltage. So and then later I set the gate voltage to 0 volts and then to 2 volts. So basically I want to look at the drain current versus drain voltage at 4 different gate voltages. These gate voltages are minus 6 volts, minus 3, 0, and 2 volts. And finally, I plot these ID versus VDS characteristics at these 4 gate voltages onto the same figure using the overlay command in Silvaco TCAD. And finally, I quit the program. So let me close this figure and let me run the simulation. Here is the structure under thermal equilibrium. We can right click on the structure, click display, and then click on this icon to display the electrodes for the transistor. So here is our substrate, here is my source contact, the drain contact, and the gate. And this is our region of interest, so I'm going to focus on that region. we can zoom out, we can look at the meshing. The goal is to include a denser meshing in critical regions and sparser meshings in regions away from the interfaces. We can look at the energy band diagram. Let me zoom in further onto this region. So we can look at the energy band diagram of this structure. So I go to Tools, Cut Line. Here I go to Display. EC of T, EV of T, electron QFL. So here is my energy band diagram on the right side. As you can see, the band gap of hafnium oxide is approximately 5.5 electron volts. Similarly, the band gap of graphene is negligible. This region is also based on hafnium oxide. Here is my molybdenum sulfide region with a band gap of approximately 1.89 electron volts. And then on the right side over here we have the silicon dioxide part of the substrate region. At this point, the program is running a sweep for the gate voltage in the range of -15 to 2 volts. And after this is complete, we can look at the ID versus VGS characteristics for the transistor. After facing a minor convergence difficulty, now it's running at its normal speed. So here is the ID versus VGS characteristics of the transistor at a drain voltage of 45 millivolts. Now you might see here that the drain current is higher at high negative voltages, and it is 0 at 0 volts, and it's also 0 at a positive voltage in the range of 0 to 2 volts. So which means that the transistor is on at negative voltages and it's off at positive gate voltages. This might seem counterintuitive initially. So, like for example, if we talk about the conventional silicon based field effect transistor, this one over here, we know that for the conventional n-type MOSFET, we need to apply a positive gate voltage in order to attract electrons from the bulk region towards the channel, towards the surface, in order to form the channel. So, which means that positive gate voltages would actually form the channel and turn on the transistor. However, in this scenario over here, we see that it's going to be the negative gate voltages which are going to turn on the transistor, the molybdenum sulfide based transistor. So I have got a good after giving it a lot of thought, I think I've got a good explanation for that. So the first thing is that molybdenum sulfide is entirely different as compared to the conventional silicon based field effect transistor. In the conventional transistor, we have a substrate layer, and minority carriers are attracted from the bulk region towards the surface. However, in case of molybdenum sulfide transistor, we don't have the substrate region from which we can actually attract minority carriers towards the channel region. We have the silicon dioxide. Electrons cannot flow from this P plus silicon layer to the channel through the silicon dioxide layer. So then how does the conductivity of this channel region modulate? How do we increase the conductivity of this channel? Which means, how do we bring more electrons to this channel in order to turn the transistor on? And I think I've got a good explanation for that. Keep this point in mind, and we are going to get back to it in a minute. This figure is from another simulation, so I'm going to close this one. Similarly, this one is also from another simulation. This one is also from another simulation. Okay, cool. Actually, I'm running another simulation in parallel, so you got some results for that as well. And I closed those results. So, so here is, I actually saved the structures at different gate voltages as well. As you can see, here is the structure at minus 6 volts gate voltage. Then here is the structure at minus 3 volts. Here is the structure at 0 volts gate voltage. And here is the structure at 2 volts gate voltage. And I want you to look at the electron concentration in the channel region at these 4 gate voltages. So in order to look at the electron concentration inside the channel region, we go to tools and then cut line. And we draw a cut line over there across the channel region. Then we go to display. And we click on the electron concentration. And then we zoom in on the channel region electron concentration. So at a gate voltage of minus 6 volts, my electron concentration is approximately 10 to the power of 20 per centimeter cube at the surface. And we also want to look at these electron concentrations inside the channel region at other gate voltages as well. So let me quickly do that. Okay, so now let us compare these numbers. So at minus 6 volts gate voltage, my electron concentration at the inside the channel is approximately, or you can say at the surface of the channel is approximately 10 to the power of 20 per centimeter cube. At minus 3 volts gate voltage, this electron concentration is low 10 to the power of 19 per centimeter cube. At 0 volts gate voltage, this electron concentration is low 10 to the power of 18 per centimeter cube. At plus 2 volts gate voltage, this electron concentration inside the channel is approximately low 10 to the power of 16 per centimeter cube. So basically the electron concentration inside the channel is decreasing as we sweep the gate voltage from negative to positive. At higher negative gate voltages, we have higher electron concentrations inside the channel, and at higher positive voltages, we have lower electron concentration in the channel. And here is an explanation for that. So let me zoom in on this region over here, the region of interest. You can display contacts as well. Here is the gate contact, the drain contact, the source contact, and the floating gate, which we are pretty much not using inside this simulation because we are not focused on the memory part, we are focused on the transistor part of the structure. And here, so now the question is, how do we modulate the conductivity of the channel? It's modulating with the gate voltages, but what is the phenomenon? Where do the electrons come from into the channel? So in order to understand that, let us look at the electric field across this structure. So we go to define contours, and then we go to electric field. So here are the electric field lines across the structure. The electric field lines are extending from the gate to the drain and from the gate to the source. And here in this region we have the graphene layer. So this layer is going to block the electric field lines because it kind of acts as a metal. So now that when the electric field lines are directed to the drain region and also to the source region, when we apply a negative voltage to the gate, so here is my understanding. Since we have a negative voltage at the gate, this negative voltage pushes electrons from the drain and the source regions, which are based on graphene, into the channel. The higher the gate voltage, the more the electrons are actually injected into the channel. And then when we apply drain voltage across this structure, it's going to result in the flow of current. So the higher the gate voltage, the more number of electrons are injected into the channel, resulting in an increase in carrier concentration. So that is my understanding and explanation of the behavior of this structure. And now finally, here are the ID versus VDS characteristics of the structure. The drain current versus drain voltage at different gate voltages. The red curve corresponds to a gate voltage of minus 6 volts. The green curve corresponds to a gate voltage of minus 3 volts. The blue corresponds to 0 volts, and this cyan color corresponds to 2 volts. So by sweeping the gate voltage from negative to positive, the drain current is decreasing versus the drain voltage. That's all for this simulation, and with more understanding I'm going to continue working on these kind of structures. It's my first time experience with these structures, and with more understanding we can actually simulate more structures. So please follow up on my YouTube channel for more videos like this. Take care until next time. Bye. Adios.